Okay guys, so we're going to start topic 3 in this video today, which is going to go over equilibrium of a particle. So we're going to introduce a really important concept in this topic that we're actually going to extend later in a future topic, and that is the concept of free body diagrams. Okay. The next really important thing, of course, is just solving particle equilibrium problems using equations of equilibrium. So both of these are super important. Both of these concepts will kind of carry on to other classes like mechanics of materials, structures, steel design, concrete design, and basically even into practice, free body diagrams, or as we sometimes call them, FBDs. Those will be a part of a lot of your future courses, so it's really important that we understand how to create these from this class, from statics, okay? So we're first going to talk about equilibrium. Okay, so what does equilibrium mean? Most people, or generally when we think of equilibrium, we think of something at rest, right? But it doesn't always mean that it's not moving. It could be a system that is at rest or something that has constant velocity, or in other words, no acceleration. Okay, we're not really going to talk about anything that is moving with constant velocity in this class. That's going to be for dynamics. Okay, when we're talking about anything in motion. In this class, we're going to stay within the realm of static equilibrium, which just is basically in terms of any object that's just completely at rest. Okay, so even though I won't always use the term static equilibrium in this class, sometimes I'll just say equilibrium. Just know that I'm not referring to particles or objects that are in motion with constant velocity. I'm referring to static equilibrium, which means they're completely not moving. Okay. Now, in order to maintain equilibrium or to satisfy equilibrium, we have to satisfy Newton's first law of motion, where we're going to say that the sum of all the forces acting on an object are going to be equal to 0, right? Because otherwise, when objects are in motion, you would have the sum of all forces is equal to mass times acceleration, right? This is not the case for this class. We don't want any mass times acceleration. We don't want our objects moving. We want sum of forces are equal to 0. We want those objects to stay still. So you want to think of designing or working on problems that include structural elements, right? So let's say we have a building. We do not want our building to have any type of acceleration, right? We don't want that building moving. We want it to stay still. So that is a static problem. That's why we want all of our forces to equal 0. And this is our most important equation in this class. We're going to use this equation in different dimensions and different ways, but this is the most important equation here. Okay, we're going to be using this equation over and over and over to solve for problems. Okay, so I've highlighted the next slide, which is a free body diagram, and I'm going to use the acronym FBD to refer to a free body diagram. Okay, so whenever you see me writing FBD, that means that it's going to be accompanied by a little image or a picture of what's happening in the system. Okay, this is a diagram basically of a particle or a rigid body. So we're going to later on in a couple of sections down the road, we'll talk about rigid bodies. Okay, right now we're going to work with particles though. And what we want to do is we want to draw a picture of this particle or this rigid body with all of the forces acting on the particle. Okay, that's it. It's as simple as that. You just want to draw the particle and all of the forces that are acting on it, okay? Now, one small step that we need to kind of take care of before we get into drawing FBDs is we need to understand what supports we have when we're dealing with different kinds of problems, okay? And I'll tell you what I mean by supports in this next slide. So we have different kinds of elements that support these forces. So for example, here, before I get into what's going on, here we have, let's say, a ceiling. I'm going to redraw this because it's a little blurry. Let's say we have a ceiling. That's what this line here represents, okay? You can think of this as a ceiling. Okay, and let's say you want to hang something from the ceiling, some type of spring and a ball system, for whatever reason, and the ceiling is fixed, right? When I say it's fixed, I'm going to draw these little lines here. That means it's not moving. The ceiling does not move. It's not going anywhere, right? Now we have this little spring that we're going to attach to it, and if I pull on the string with some force F, the spring is going to elongate, and then when I let go, the spring is going to compress. It's going to shorten. right? So I have some initial or at rest length of the spring. I have some deformed length of the spring when I pull on it, and then I have a continued deformed length once it goes back and compresses. So what I can do is I can use Hooke's law, F equals Ks, to represent any type of spring that I have in terms of support. Okay, so F is equal to Ks, and remember K is our spring constant, which tells us how elastic that spring is, how strong or how stiff the spring is. Okay, the next type of elements we have are cables and pulleys. Okay, so if I have a cable or a pulley, I'm going to represent the force in that cable with a T, T for tension. Okay, and this is a pulling force, right? So if you can imagine if I have some type of weight here, let's say I have a weight here and I have another weight here, and they're both pulling down with their, mg weight, W equals mg. You can see how these cables are going to be in tension. So we say the force in those cables is just T, or the tension force. Okay. The last type of support we'll talk about for now, we have a couple of other supports we'll talk about later, but for now, the last type of support we're going to deal with for particle equilibrium are smooth contact or basically the normal force, right? So what I mean by that here is we have a smooth contact surface here. So of course we're going to have a perpendicular force acting on that object or that smooth support. And then we're assuming, or this picture has some type of cable system or pulley here, pulling force. That's why we have T. That's from the cable or pulley. But we're also going to have this N, which is the smooth contact or normal force that we get, right? It can be at an incline. It can be at a 90-degree angle. It can be at anything, okay? As long as it's perpendicular to the surface, right, that it's acting on. So this is perpendicular to that surface there, okay? So let's go ahead and do an example. So we have a sphere here, and we're given a mass of the sphere of 6 kilograms. And what we want to do is we want to draw a free body diagram of the sphere, the chord CE, and the knot at C. Okay, so what we want to do is we're going to first start by drawing the free body diagram of just the sphere. Okay, so what we want to do is, because the problem is asking us for the free body diagram of the sphere, we're going to isolate the sphere. Okay, we're going to isolate the sphere almost like you want to make a little cut. And you want to say, now that I've made this little cut, this little environment of the sphere, what forces are directly acting on the sphere? So I'm going to come over here, redraw my sphere, and I'm going to start. So the first thing I know is the sphere has a mass of 6 kilograms, right? So I know that I'm going to have this force due to gravity, right? This weight, which is equal to mg. And in this case, that W equals mg is 6 kilograms times 9.81 meters per second squared. So I'm going to move all this down a little bit. I end up getting, whoops, didn't like that. It's too much work for it to move down. Let's see what happened. Okay, well, I guess I'm going to have to draw that again. So bear with me or skip through this part here. But basically, this is where we're at. W is equal to mg. M is 6 kg. 9.81 meters per second squared, and I end up with 58.9 newtons. Okay, so that's my W. You don't need to write out the calculation here. You could just go ahead and write 58.9 newtons. I just wanted to write it out to show you where I got it from. Okay, so that's the first part. Now, the next thing is it erased my little cut too. Let me go back to my little cut here, my little isolated cut. Okay. The next thing we have here is, you can see here at the cut, I'm cutting the chord CE, which means I'm exposing a force there that's connected to that mass or that sphere. So I'm going to go ahead and draw a straight line here, and I'm going to call that the force in CE. You can call that the force in CE. You can call it tension in CE. You can call it T. Whatever you like to call it, you can call it. I'm just going to call it FCE. Okay, last thing is I have two contact surfaces. I'm drawing them in purple right here. I have two contact surfaces, so I know I'm gonna have to have two normal forces, one coming in from this direction. I'm gonna call this normal force A. There's an A here, right? And I have another normal force. You can call it normal force 1, normal force 2, whatever you want. I'm just gonna call it A and B, okay? And that's really it. So we have FCE. Again, FCE is the force of the chord acting on the sphere. So this is the force of the chord. You don't need to label these for your FBD. I'm just doing it this time because this is new for us. But you probably should put that we're drawing our FBD like this. Okay. And then, of course, the N, this is the forces of the smooth planes acting on the sphere. So these are the normal forces. And then our 58.9 is the weight or gravity acting on the sphere. Okay, so this is it. This is our answer for the FBD of the sphere. Okay, our next free body diagram is going to, so I should probably put here sphere. Our next FBD we're asked to draw is that of the chord. So I'm going to come back to this picture here. I'm going to erase what I had drawn, and I'm going to come now and just draw the chord here. Okay. So what happens is this is a break in the chord, this is a break in the chord. So really I just have this system here. So if I were to isolate that chord, this is a chord, all I really have, I'm getting the FCE from the bottom. And I just have FCE in the top. All I really have for the chord is that tension force. Okay, so this is basically the force of the chord CE, and this is force of knot on CE. So I really don't have anything else happening here. That's pretty much it. Okay, and then the last step is the knot at C. Okay. Actually, before we get there, I do want to say one thing about this. So in this system here, we notice a couple of things. We notice, or we know that we have to abide, or we have to satisfy Newton's second law, right? Of equal and opposite forces. So that means here, we know that FCE at the top, right, has to be equal to, what's happening here? I can call this FEC so that I can differentiate them at first. The reason I just named them the same thing is because we know that FCE has to be equal to FEC, right? The pull on the chord has to keep this tension so it doesn't collapse. So to maintain equilibrium, right? Imagine you guys imagine you're doing a tug of war with one of your friends. The only way that system is going to be completely in equilibrium is if you're pulling the same amount. If person A is pulling the same amount as person B. That's what we're saying here. These two have to equal each other, FEC and FCE, in order to maintain equilibrium and satisfy Newton's second law, right? Okay, so now let's move on to the chord. I'm sorry, not chord, the knot. We did the chord already. And what we have here is we have this little knot. I'm going to isolate this little knot here, right? And what I get is, here's my little knot. I have a spring force. I'm going to call this FCD. And FCD is the force of the spring. This is K times X, right? I also have this force in this direction, which is, I'm going to call this call this FCB. Okay. And I also have this FCE, right? Or FEC, whichever you want to call it. This is the force of the chord on the knot. And that's pretty much it. That's the FBD. Okay, so those are my 3 free body diagrams. And one thing to note here is, as you can see for the FBD of the knot, the weight of the sphere does not directly act on the knot, right? Instead, chord CE subjects the knot to this force. So I'm going to show you what I mean by that. The weight is in the same direction as FCE. Then FCE transfers that weight to the knot. So we have the weight here, transfers to the cable here, transfers to the knot, and then throughout the rest of the system. Right? Okay. So let's move on here. Now, we're first going to talk about coplanar or 2D force systems, and then we're going to get into 3D. Okay, so if a particle is subjected to a system of forces that lie within the XY plane, one easy thing we can do is we can resolve these forces into their I and J components. So this is kind of similar to what we had done previously using vectors. We use the X and Y directions, and we use those unit vectors I and J to resolve each vector into their respective components, and we did that with forces as well. And now what we're going to do is we've already done something similar with vectors. We're going to say sum of forces in the X have to equal 0 and sum of forces in the Y have to equal 0. So all of these forces acting on a particle, however many they are, all of the forces that I resolve into the X direction need to be 0. All of the forces I resolve in the Y direction need to be 0. Okay, so I'm going to show you an example of that here. This is very similar to what we've already done with vectors. We're just now using them for forces. So determine the tension in cables BA and BC necessary to support the 60 kilogram cylinder. The first thing I want to do is I want to draw the free body diagram here. Okay, so I could draw a couple of different FBDs. I can first start by drawing the FBD of the cylinder. Okay, so I have the cylinder, let's say here, and all I really have is the weight of the cylinder, right? Which is going to be 60 times 9.81. Okay, and then I have that tension in the cable above, so I'm going to call this FBD, right? And you can see here, now, from sum of forces in the X and Y direction, I have no forces in the X, so I'm going to sum forces in the Y direction, set them equal to 0, and I get that FB, you can also call this TBD, tension BD, whichever you like. FBD has to be equal to 60 times 9.81. All right, so I've already solved for the tension in that cable, and I get 588.6 newtons. Okay. It's pretty simple. Now I'm going to move on, and I'm going to draw the FBD at this point here at point B. Okay, so FBD not at B. And here I'm going to draw my force FBD, which is 588.6. Okay, and then I also have a TC or FC, whichever you like to call this. I'm just going to call them TA. You can put any letter there you want. Now I'm going to draw my X and Y axes here so I can resolve everything into their respective components. Right? And they're already giving me in the problem, this is a 45-degree angle, and that the TA force makes a 3, 4, 5 triangle. So I'm going to go ahead and continue. And I'm actually going to solve this one just without having to use Cartesian vector notation. I'm just going to directly solve this because it's actually already very simple. So sometimes you can put everything into I and J, or you can directly just use the X and Y directions. Okay, so you'll get the same answer either way. So I'm going to start here by saying the sum of the forces in the X direction have to be 0. I'm going to say the right direction is positive. Okay, I'm going to come here. I'm going to start resolving these into components. So if TC is going in this direction, I'm going to have TC cosine 45, TC sine 45. And then in this direction, I'm going to have well, my lines are a little crooked. Let's see what's happening. There we go. TA times the component 4 over 5. And then here, of course, I'm going to have TA times the 3/5 component. So for the x direction, I'm going to highlight all the forces in yellow. So I have this and this. For the y direction, I'll use the green. I have this, and I have that. Okay, so everything in yellow needs to be added in the sum of forces in the x direction equals 0. So what do I have here? I have TC cos 45 minus, because the TA is going the other direction, equals 0. Okay. And I can simplify this a little bit. I can say TA equals 0.8839 TC. Okay. Can't solve anything really, but I'm getting there. Use my second equation of equilibrium, and this is going to sum everything in green now. So I have for the green TC sine 45 plus 3/5. I'm going to directly, actually I'll write it out and then I'll directly plug it in. And then minus the 588.6 equals 0. And now what I'm going to do is I'm going to take this and plug it in for TA here. Okay, so I get TC sine 45 plus 3/5 times 0.8839 TC minus 588.6. And I can directly solve for TC from that above equation. I get 476 newtons. And then I can solve for TA by just plugging it back in, and I get 420 newtons. And these are my answers. Okay, so pretty straightforward. You can make as many free body diagrams as a system as you need to solve for. Once you guys start doing more of these, you'll really easily recognize that the tension in this cable is actually just the weight of the cylinder without having to make an FBD there. You can probably just get right into making this free body diagram. But it takes a little bit of practice, so take as much time as you need in the beginning problems, and you'll see yourself slowly getting quicker in the analysis for the future problems. Okay, let's do another example, a little bit more complicated because there's a spring, but still very straightforward, very similar to the one we had just done. Okay, so here we want to determine the length of the cord AC so that the 8-kilogram lamp can be suspended in the position shown. The undeformed length of the spring is LAB or 0.4 meters, and the spring has a stiffness of 300 Newton meters. So now I'm going to do this problem without doing the free body of the lamp and then the free body of the knot at A, and show you guys what that looks like. So I basically know that the lamp's weight is 8 kilograms times 9.81 meters per second squared, and I would get 78.5 newtons. So I'm going to directly go ahead and draw the FBD of the particle at point A. And I know that that force is going to be pulling down the same weight, which is 78.5 newtons. So I directly can just go into that FBD. Now I have another force here. I'm going to call this, whatever I call it, TAB. I'm going to call it FAB. And then I'm going to call this force here TAC. Again, does not matter what you label these forces, as long as they're in the right directions. Okay, so first thing I'm going to do, actually, I'm going to go ahead, right, and sum forces in the x direction. I only have to resolve TAC into components. And I know that this is a 30-degree angle right there. So I'm going to go ahead and directly say TAC cosine 30, TAC sine 30. I'm going to do the same thing. X forces are going to be highlighted in yellow, and Y forces will be highlighted in green. Okay, so sum of forces in the X. I have yellow force, right? FAB minus TAC. And then I have sum of forces in the Y. And this is going to be the addition of all of the forces you guys see in green. So TAC right? So I can come directly and solve for TAC, and I get 157 newtons. And then I can plug that in and I can solve for FAB as 135.9 newtons. But now I want the stretch in the spring. So I haven't really gotten what I want yet, but I'm getting close. So I want the stretch in the spring, and I know something about this force here. I know that this is the spring force. And I know that that FAB, which is a spring force, is equal to K, the stiffness in AB, times SAB, which is that deformed length, right? How much it deforms. So I'm going to plug in here what I have. I have 135.9. The K is given in the problem. Where is it? Right there, 300 Newton meter. This is Newton times SAB. And I get that SAB is equal to 0.453 meters. And remember, this is how much my system has deformed, the stretch. How much has it stretched? So if I want the new length, this is basically, write this down here. Okay. So the new length, to get new length of AB, I need to take this plus that little change, right? So I get 0.4, this is my initial length, plus 0.453, and I get 0.853 meters, okay? But now, let's go ahead and look here at what they're asking. Undeformed length of the spring is 0.4 meters, right? And the spring has stiffness of this. So the horizontal distance from C to B, total, this distance is 2 meters, right? So what I really need to do, what I really need to get is this 2 meters, which is equal to LAC cosine 30 plus the 0.853 meters, and this is my final answer, which is LAC. I want this distance here. This new distance here. Okay, because remember, I'm trying to find the required length of chord AC. Okay, so what I need to do is plug in here the 0.853, and I get LAC is equal to 1.32 meters. So this is from geometry. After I figured out those stretches and those forces, I can get that final length of LAC after the system has been loaded. Okay.